Yeah. Cool.
Okay. Yeah, it's work. Hi, good afternoon, everyone. To begin, I just want to express my gratitude to Professor Betos. Yeah. And last month in summer event at UCL East, we met the first time and had a very enjoyable conversation. And from that, uh, Nadia invited me come here and share some of my work I have been doing. Yes, and since that, this invitation also gave me a chance to reflect on about my own research directions and organize some of work I have been doing. Yes. Um, so today I'm happy to share that with you all. For those who may not know me, I'm Wenbo Zhang, a PhD candidate from South China University of Technology in Guangzhou, currently visiting UCL and working together with Professor Jigmo Han Chu Han. Today, I will walk you through a progression from sensing movement to uncovering the deeper physical evidence and organizing that evidence into body states, bringing those states to user interaction, and finally, toward into the intelligence wearable system. Yes, before I introduce these individual projects, let me start with the main idea behind this talk. Yeah, we all know wearable states and that like wearable system can already quite good to telling us what a person is doing. They can recognize running and estimate the speed and count steps and also can can describe some movement pattern. But knowing what the movement looks like still not the same as understanding what's happening inside the body. Maybe two movements look like almost the same, but under brace, the muscle effort, and the loading and the compensation or fatigue may be very different. So the key point is similar movement can reflect very different internal physical states. And this is a gap I want to explore today. So if observable movement is not enough, what exactly is missing? Yes, wearable device can collect many signals like IMU, EMG, PPG, pressure, and also vision. But these signals are only evidence. They do not directly tell us what is happening inside the body. This is the representation gap. What we need in the middle is a body state layer. For example, activation, loading, force, and so on. Once the system understands these states, it can provide useful support, such as feedback, regulation, or intervention. So the key message is sensor signals are evidence about the body, but they are not yet the body understanding. This gave us the overall research path for today. I organized the talk into a simple progression. We begin with the surface. Yes, we begin with the surface movement like pose, activity, joint, and then move to underlying physical evidence, muscle activity, the balance, the force, and also with body pressure. And the next step is organize this to the body state organization. They build the structured body states, including intensity, and asymmetry. After that, we ask this state can become a actionable support through perception feedback intervention. So the overall direction is from motion to evidence to states and for the action. Yes, the first question is about the movement. How does the body move? We know the high-end system like motion capture setups, qualisize, Wacom, and actions can reconstruct our body movement, but they are complex and expensive. Our research asks, can we recover full body movement using only a small wearable sensor? The goal is to enable lightweight system can be used in daily life when we fitness, support, and even though we can in-home rehabilitation. To explore this question, I will briefly introduce press impulse. Press impulse use a small sensor, just like insole, two insole and the rest IMU. Together, for the lightweight for body post estimate. Just like our body right and wrong, we use the two leg. In this paper, we also observe this idea. We use the real date and the virtual date and stand on two legs. On the real side, we collect motion and pressure signal using the small insole and the rest IMU. On the virtual side, we use large language model to generate device motion data from pre-training. These two types of data and then combined in our body estimation network to predict the 3D joint. With the lightweight setup, we achieve an average joint position error of about 7.75 centimeters across different activity. We collect 25 participants and test in 7 different activities like walk, like squat, and also we test in the badminton and basketball, just like the easy movement. The main challenge is that with only the small and the spread sensors, how can we keep whole body consistency? Yes, we split the body as the lower upper body and the lower leg, the two trying, and use the global feature extractor to combine these global features. Press impulse can support in the sport science and health monitor and VR. It shows that we can use the surprise wearable system recover full body movement. But movement alone is not enough to understand the body. We need deep evidence. Now move from the movement to evidence. The question is what physical evidence lay beneath movement and can wearable system recover it? I will first introduce kinetics. Pose is still mainly about kinematics like joint angle, trajectory, posture. But it just told us what the movement looks like. But kinetics goes deeper. It's about muscle activation, force. It helps us to understand the movement is how to predict. Kinetic sense tries to recover this deeper information from surprise variables. First, the system uses 3 IMUs and pressure signals to reconstruct the 4 body pose, and then use the pose, motion, and pressure information to estimate lower limb muscle activation. In short, movement and pressure offer indirect evidence of muscle activity. So surprise variable sensing can recover patterns beyond the pose alone. Here, the solid line are the ground truth and the dashed line are the prediction. We can see that the model follows the main muscle activation patterns across different movements. We test in the squat and jump and left right kick. This includes different movements like priority and also asymmetry one, because they have left or right kick. So the system can capture activity muscle dynamic. Muscle activation is one type of the evidence. Another important type is plantar pressure, because when we running, when we do some training, our body have the pressure in the ground. So plantar pressure provide rich information about the contact, the loading, and weight transfer. But pressure systems are often expensive or difficult to deploy in every day. So motion sensors like IMU are easier to move, to wear. So our question is, can use the surprise wearable sensor to recover the plantar pressure. If this is possible, we can provide richer biomechanical feedback using simple sensing. This is the main idea behind motion to price. Motion to price starts with IMU signals from common wearable device like earphone, watch, or the smartphone. The model learns motion feature and adapts them to different users. We also added physical constraints to make the prediction pressure is physical reasonable. Finally, the system reconstructs plantar pressure maps over time. Also, we compare the prediction results with the ground truth. The model can recover center of pressure patterns and ground reaction force trends and the spatial pressure distribution. The prediction is not perfect. We can see they also have some mistakes. So, but it follows the main temporal, yes, and the spatial patterns. Like we also use the hand map to show. So wearable sensor like the IMU can recover useful plantar pressure dynamic. We then ask whether the same idea could extend beyond guide to the wrist and hand. Watch force estimate hand force from signal collect at the wrist. We use the PPG and IMU signal from a wrist device. The system supports both force level classification and continuous force estimation. In our study, we use the 16 participants and 5 hand actions to classification. The general classification accuracy was about 18.6%, and for the personalist is about 88%. The key point is that the physical effort can be inferred indirectly, without placing a sensor directly at the point of force, like the hand pose. At this point, we can recover several useful types of physical evidence. Watch force estimates hand force, and kinetic sense estimates the muscle activation, and motion to price construct plantar pressure, but those outputs are still fragmented. So the next question is how can we organize them into a meaningful body state representation? This brings us to the next part, body state. What should a wearable system represent about the body? This is the main idea behind the halo. Instead of predicting sprite quantities, halo organizes activation and loading into a structured body state representation. So halo is not just another prediction model, it's a way to describe how the body is organized during movement. But why is this representation useful? The two movements may look very similar. We can see trail A and trail B. In the different floors, we can see the movement is the same. Like the joint, and also we can use the knee flexion angles is nearly. But inside the body, muscle activation and loading may become very different. One movement may require more muscle effort. Another one maybe place more load in one side. So a similar movement does not imply similar internal organization. Halo is designed to reveal this hidden difference. Halo states from a splice wearable setup using two thin IMUs and two EMG channels. For these signals, we build a body structured representation, use the GNN. And this representation connects the observed sensor location with the wider body structure. We then model how these signals change over time. Finally, halo produces four main dimensions: activation intensity and asymmetry, loading intensity and loading asymmetry. Together, these dimensions form a structured body state. But how can we build and validate these states? During the data collection stage, we use rich sensing, include four lower body IMUs and multi-channel EMGs. And also, we collect the plantar pressure and motion captures. These signals help us to construct and validate the halo state targets. But during deployment, we only use two side IMUs and the quantitative EMG. So the principle is simple. Rich evidence during collection, but sparse sensing during deployment. Here, we compare movements like that look similar on the surface. This is two people surface movement about squat. This visible movement be close, but the underlying activation and loading patterns can be different. Like this one is A, and this one is B. The yellow is another one. It's the black is another one. So it's very different. But the trail, we can see the movement maybe the pattern is similar. Also, halo gave us a structured representation of hidden body states, but representation alone is not the goal. The next question is how these states can enter the user action loop. Muscle Sense explores this question through real-time audio feedback. Muscle effort is difficult to see and difficult to feel accurately. User may know that they are moving, but they may not know whether the target muscle are working or as intended. Before a user can regulate muscle effort, they first need to perceive it. This is the main idea behind muscle sense. So we ask whether sound could make the hidden effort easier to perceive. Visual feedback is useful, but it has some limits. Like user need to look at the screen. This can take attention away from the movement. And it's also difficult to capture the visual feedback continually during our exercise and training. But audio is eyes-free and continuous. It allows users to hear changes in muscle effort while they are moving. And audio keeps the feedback inside the actions. Before building the final sound mapping, we first explored how people understood different sound changes. We used the formative study to compare different sound design and understand the user's mental models. The result gave us several design principles. The continual effort should use smooth and gradual sound changes. Important events should use short and clear accent. So the sound design was guided by both perception and actionable. Based on those design principles, muscle sense maps different muscle states into different sound features. The muscle intensity is represented by pitch. The muscle asymmetry is represented by the sound contour. And the co-contraction events are represented by short sound accent. In this way, hidden muscle states become something the user can hear during the movement. And we then deploy this system in real time during exercise. People just collide where the two bond in the lower limb, and just when we do some training, just collide the earphone, and we can do the movement, hear some sound is mapping with the muscle sense, muscle activation. And also, we test in the real time. The overall latency is about 382 milliseconds, which is fast enough because they also have Bluetooth delay. People can use this sound feedback for continued adjustment during exercise. In our study, users reported better awareness and better perceived control of their muscle effort between the visual and just to themselves feedback. The main contribution is not only sensing muscle activity, it's closing loop between sensing, perception, and action. Now we move from interaction to intelligence. The question is, how can wearable system reason over body state and provide the personalized support? This is the idea behind Hello Agent. Raw signals are difficult for an agent to understand. Structured body state are clearly. They tell the agent what is happening inside the body. This makes reasoning and feedback more useful. Hello Agent built on this idea. We just use the wearable signals like build like hello state different for dimensions and build the structure body state memory for the personalist. So we also test in different parts. Hello agent start from structure body states, activation, loading, asymmetry, and it also uses personal baseline and recent history, just like memory. The agent then reasons about the current situation and provide continuous feedback. We keep the agent model the same and only change the input representation. So does a better representation improve the agent reasoning? Yeah, there's some different part to show the result. Before evaluate the agent, we first check whether hello state is gradual in the wearable evidence. On the left, lower deviation means better agreement between hello state and the source evidence. So cause shows the best, but the set down is more challenging. In the middle, most of the error comes from the loading intensity, especially during set down. On the right, two squad segments have very similar movement with correction of 92%. Conclude knee angle correction and between the segments, the different segments. But their activation and loading evidence are different. That's the hello states provide this difference. So hello can reveal hidden body state difference and the surface motion alone may miss. Yes, let me now bring all the project back into one research genre. We start with movement using sprite wearable to recover full body pose, and move beneath motion to recover richer physical evidence, including muscle activation, the plantar pressure, the hand force. And hello organize this evidence into structured and interpretable body states. Also, muscle sense makes hidden muscle effort perceptible and actionable. Finally, hello agent use body state and memory and personal context to support intelligence reasoning. Across these projects, the goal is the same: to move from recognizing movement to understanding and action on hidden body state. This leads to broader vision behind my research. My vision is simple. Wearable should not only observe the body, they should help people understand what the happening inside the body and how to adjustment in the loop, and also maybe can useful in different scenario, like we do some training in gym and do some fitness. Also for the we can, sorry. And to do this, they need to be low burden and interpretable and personalized and also safe. Looking ahead, I see these three directions. First, we need to move beyond the controlled tasks, because for the past project, some scenario we also need in the control environment in laboratory, but the study more real world and daily life activities we must to extend. Second, the body states model should become more personal and adapt to each user over time. Because every different people have the different habits in this do training and like running and so on. Different people have different habits and the body have different hidden state. So the personal and adapt to each over time is more important. The third, wearable agents should be safer. They should know when to give feedback and when to remain silent. So the next challenge is not only so the next challenge is not only better prediction, but trustworthy support in the real life. With that, I would like to finish here. Yes, thank you very much for your attention, and I hope you enjoy this talk. You can scan the code to see more about my research. Connect with me on LinkedIn. Yes, for the finally, I want to also thank for the Mark to arrange this talk. Thanks again for Professor Nadia. Yes, thank you a lot.
So, thanks for this very nice talk. Are there already some questions in the room? Who would like to start? You?
I can start. So it's very interesting to see that you mentioned that you part of your study studied the sound effect for that, but given that you already have the chatbot, I just want to know, have your study showed that the difference between providing a sound effect versus just the chat with the chatbot, how people would like to receive their feedback from this agent?
Yes, that's a good question. Yes, because they all know the large language models can have the many knowledge about the training, sports, everything. So we also want to build the agent to give some feedback and not only about the sound for people to perceive, but the next step. And also we've knowing is to add it with the large language models, like use the sound to feedback and give some talk. Maybe we can also ask the large language models what I'm doing. Can you tell me what is wrong? And for my next step, how can I to adjust? So we can build like a virtual people, like just like the trainer or different. Yes, I for knowing I just doing this one because I think added with the large language models or agent is meaningful and will helpful in the different scenario for our do some basketball training and rehabilitation. It can understand what I'm doing and can to give some different part the meaningful advice to adjustment. And also, just like the hello states, because I can structure the body state, so the answer from the LLM can more accuracy about my body states. Yes, thank you.
One more question. Is that you used the multi-sensor system. So I wonder, how did you deal with the problem if one sensor is telling, for example, on the same movement, let's say on the same like with a squat, what if the like the foot pressure says something different compared to the EMG or the camera or you use? So what if the two sensors are conflicting with each other? How your system navigate through this?
Yes, in my project, I just for collect the data from the timeline for the same beginning and the same end. We can use the time to calibrate the different sensor. And if the data have the conflict, I'm not totally to understand what's the conflict in the different wearable sensor, because the foot pressure, just like insole and the IMU, maybe we can collect in the watch, the small watch and the phone. They just describe the different things, different part about our body. So I think the data actually not conflict, but way to precising the different sensor maybe have different way, just like pressure, maybe they have some, we also use the mapping to the head map. Yes, use the CV to mapping to the head map. And for the IMU, maybe we can just, so I just want to say the different sensing, different sensor just describe the different part. So I think the data actually is not conflict, but we can adapt different precising method for the different sensor.
I think my question is on the next step, which is to the person, like the meaning of the movement.
Yes.
Like the two things may be in conflict with each other. Like the EMG, if you're just using, for example, if you're just using EMG to inform the AI or the agent,
yes,
it may generate, oh, you need to sit tighter. But if you are using the, let's say, the foot pressure, it may tell, oh, you need to sit straight up.
Okay,
So it's a bad example, but you get what I'm saying.
I get it.
So on
the interpretation may be completely, one may be wrong or.
Yes, I get it. So for me, I think for the raw data signal is it's just for the evidence, because the sensor about the EMG just for the muscle activation, and the pressure is just for the body contact with the ground. I think we can use the different part sensor to build our body state. So just like hello, I use the sensor for the step to build our body structure states, and maybe for the next step we can connect with the camera for the scenario context to wholly describe what we are doing, and not only for the EMG, maybe the left leg muscle is high level, and so you need a rest, but it's part. I think we can just first to build our full body state and connect with the context. Yes, thank you for your question.
There's an online question by Federico Coleccia. Thanks for the nice presentation. What is your plan for moving from controlled environments to everyday settings?
Yes, because just like for rehabilitation, people need to control environment, like a laboratory. We use the camera and different angle sighting, and for the plant pressure must use the expensive device. I think this environment is a control. And we want to build the wearable system, just use like our daily life the device, like phone, like wearable, and like also earphone, the small glasses. We can do not influenced by the environment. We can in home and inside, in outside. So I think this is extended to daily life, not only in the controlled laboratory environment. Thank you for question.
If I were to use this tomorrow, is it available? Can I use your approach? Because I think it's very interesting and could be nice extra data that I could then also maybe, give you for your next experiments. Are these approaches open source, or can I ask you, are you willing to give it to other researchers? What are your thoughts there?
Yes, and maybe I will open source about my project, and also like different time. Today I wear the system can do it better, but if tomorrow the system is not work, what can I do? So just like I say for the next step the personalized context is also important. We can, for the one person, to collect the mode date for the personality and the different part, because one person is may not have many distinguish today and tomorrow. So we can collect the one person more different activity date to training the model, and we can build a personal model. Yes.
Cool. Thank you. Are there other questions?
I would have a question about the future work, because I thought it discussed about the kinetic and kinematic, the difference. Yeah, so we usually think the kinematic is the driven for the kinetic is the driven of the kinematic. So do you think from if we collect enough data by the wearable device, we can finally build some like the neural representation, so we can predict the kinetic directly from the kinematic we observed by like video or photo?
Yes, I think it's can doing, because for me, I think the kinematics is also for the we can see the evidence is our body, but the kinetics is inside hidden. But it's the same line, it's the same timeline in our doing some activation in the movement, just for different part. Just like I say, the kinematics is the observable part, and the kinetics is the body hidden states, but they are together to build our body doing. It can looks the kinematics is movement looks, and the kinetics is what happens in our body, inside our body. Just like this one, I also will build there you can see we want to build our body like the blue is used IMU. Sometimes IMU can only to describe our pose and the position, and just is about kinematics. And the right is about the muscle activation. It's about kinetics. Sometimes we can combine this side, and they have the describe the same things what we body doing. So I think they have some mapping inside. So for your question, I think we can directly use the IMU, just like kinematics, to use neural network to mapping for the kinetics. It's work.
Sorry, I have following up questions. For example, if somebody have the imbalance between the muscle of the two
Yes.
legs, do you have some like experience? There is biomechanical evidence about you can map from IMU to the muscle signal?
So the first step, that's why I want to explore the kinetics, because only use IMU, sometimes we see the movement is similar for the pose, because we can use the camera and use like IMU, we can build the body match pose. From the pose, if the different leg have the different just like imbalance, from the pose we can see the different pattern. But if we added the flat pressure, because if one side is highly pressed from the head map, we can see different the features. If only use IMU for or camera to build the kinetics, I think it's difficult. because I also want to use different, just a similar device, IMU. I think IMU is the most easier to wear, but only use kinematics to direct reconstruct the kinetics. Maybe for the large language models, I think maybe it can do the something, but it's difficult. But if we can add it the pressure or muscle activity, it can do it.
Thank you.
Thank you, question.
There's one more online question by Fatai Aziz. Thank you for this great presentation. Did you evaluate the model in a data missing scenario? So for example, what happens if data from one of the IMUs is out of battery or losing signal? Does this still work?
Yes, thanks for your questions. And also, I test in this different size setup for the wearable sensor. For the first time, just like, okay, this one. We use the price, and also in Solo have the IMU and the rest IMU. We to distinguish the different setup, like the foot not added IMU, only use the hand IMU. Can the network is do it better? But from the result, if we lose some part, the result show the pattern is badly. So that's why we added the rest IMU, because it's connected with our upper body. And for the in Solo IMU, is describe how our leg and the foot moving. Yes, thank you.
Cool, then let's thank our speaker once more.
Thank you.